Welcome to Brain Vision.
Apply for part A the conservation of energy or mechanical energy. So energy initial equals energy final, and we get that the potential energy initial equals the final kinetic energy of the center of mass plus the rotational kinetic energy. We can say here mg d sine of theta equals 1/2 times the mass times velocity at the bottom squared plus 1/2 times the moment of inertia I times the times the angular velocity at the bottom squared. We can then say that mgd sine of theta, this is going to equal 1/2 mv bottom squared. This would be plus 1/2 times moment of inertia mr squared multiplied by the velocity at the bottom divided by r quantity squared. And essentially, this would be equal to the mass times the velocity at the bottom squared. And so for part A, the velocity at the bottom will be equal to the square root of g d sine of theta, and we can solve. So this would be the square root of 9.80 meters per second squared multiplied by 5.60 meters multiplied by sine of 17.5 degrees. And so this is equaling 4.06 meters per second. This would be our answer for part A. For part B, the total kinetic energy at the base of the incline is the same as the initial potential energy. So this would be mg d sine of theta. We can solve. This would be 0.545 kilograms multiplied by 9.80 meters per second squared multiplied by 5.60 meters times sine of, again, 17.5 degrees. And we find that the final kinetic energy at the bottom, the total final kinetic energy, would be equaling to 8.99 joules. This would be your answer for part B. For part C, we then know that the frictional force supplies the torque for the object to roll without slipping, and the frictional force has a maximum value. So we can say that the object rolls without slipping. We know that the angular acceleration would be equal to the linear acceleration divided by r, and we're going to use Newton's second law for the directions parallel and perpendicular to the plane, and then we're going to apply the sum of the torques in order to solve for the coefficient of kinetic friction, and so we can, or the coefficient of static friction, and so we can say that here the sum of torques would be equaling force of friction times r. This would be equaling the moment of inertia times the angular acceleration. This would be mr squared times a divided by r. So this is equaling the mass times the linear acceleration times r. We then know that the force of friction is going to be equaling the mass times the acceleration, and the sum of forces perpendicular would be equal to the force normal minus mg cosine of theta. And so this is equal 0, so we know that the force normal is then equaling mg cosine of theta. We know that the sum of forces parallel would be equaling mg sine of theta minus the force of friction, and this is equaling the mass times the acceleration. And so the force of friction would be equaling 1/2 times mg sine of theta. And now we know that for part C, the force of friction must be less than or equal to the force of friction static max. And essentially, we would have 1/2 mg sine of theta is going to be less than or equal to the coefficient of static friction times the force normal, where this is equaling the coefficient of static friction times mg cosine of theta. And so we know that the coefficient of static friction must be greater than or equal to 1/2 times tangent of theta. And so the coefficient of static friction minimum would be equaling 1/2 times tangent of 17.5 degrees. This is equaling 0.158. So the minimum coefficient of static friction would be 0.158. That is the end of the solution. Thank you for